Okay, we're going to bring section 5.3 and chapter 5 to a close here today with this video. Yesterday we learned the test that you could show to prove that two events are independent. And that's showing, given that one event has occurred, the probability of the other event occurring is actually just the same thing as the probability of that event occurring. Okay, if those are equal, the two events are independent of one another. If those two probabilities are not equal to each other, then it means those two events are not independent. They are somehow linked together, affecting one another's probabilities. Okay, so we're going to kind of pick up where we left off yesterday and try that similar test here. It's asking if these events are independent, that someone is a junior and that they would get an A in AP Calculus. Okay, so what we're needing to show is we are needing to show that the probability, and the order of this can be whichever you like here. We'll just say the probability of getting an A in AP Calculus, given that you are a junior, would have to be the exact same probability as getting an A in AP Calculus in order for these two events to be independent of one another. So we're going to use the table here. We're going to go ahead and fill in what the probability is on the left side, that given that someone is a junior, so we're looking at that row there, we're talking about 12 individuals, so that's my denominator. What is the probability that a junior would get an A in AP Calculus? There were 7 of those 12. Okay, now we're going to take a look at just overall, what is the probability of just getting an A in AP Calculus? We're talking about all 33 individuals now. Those who got an A in AP Calculus would actually be referencing this column here. So we're talking about those 16 individuals. Okay, and it's always a good idea to kind of change these into decimals just to make sure that these aren't actually the same number. Okay, and clearly we can see that these two probabilities are not equal to one another. Therefore, these two events are not independent of one another. Okay, let's try another one here. We want to check to see if being a senior and getting an A in AP Stats, if those two events are independent of one another. So I'm going to just say, given that someone is a senior, we're going to find the probability that they would get an A in AP Stats. If these two events are independent of one another, then that should also just equal the probability of getting an A in AP Stats. Okay, I'm going to fill that side in first. That's 33, and I believe that out of the 33, the number of individuals who got an A in AP Stats is 17. And then over here, we're going to say, given that someone is a senior, so we're talking about that row where the total is 21, the probability that they are getting an A is 12 out of 21. Okay, if I change those into decimals, I can see that it's close, but it is not exactly the same number. Therefore, being a senior and getting an A in AP Statistics, those are not, whoops, I didn't spell that right. Those are not independent of one another. Okay. All right, so on the next page, we're going to look at a special rule here for the multiplication rule. Okay. This is a situation where if A and B are independent of one another, okay? So you'll notice that it starts out here, if A and B are independent events, okay, then the probability that A and B both occur is actually just the probability of A times the probability of B. And here's the reasoning behind this. I've replaced this notation, and what this row is right here, it's the conditional probability formula resolved for the intersection of events A and B. So this is the formula on the formula sheet. It's just rearranged. Okay. So if we know that A and B are actually independent of one another, remember the test we've been doing, we've been saying, well, if they're independent of one another, then really the fact that A occurred first is not going to have any bearing on what the probability of B is. It should just be the same thing as whatever the probability of B itself is. So you can see I have replaced that with just simply the probability of B. Okay, and that's where we're getting this from. But please be very careful. You cannot use this formula for intersection unless you know that A and B are actually independent events of one another. Okay, so we have in this box a little bit of a summary. It mentions here, if we know that two events are independent, then all of these things are true. Okay, this is saying that B is not affecting A's probability, A is not affecting B's probability. Down here, this is just another way of saying this. Whether B happens or if B doesn't happen, it has no effect on A. So these two probabilities are equal to each other. Given that B did occur first or given that B did not occur first, it really doesn't matter because it's not impacting the probability of A. Okay, that's what we mean when we talk about events being independent of one another. Okay, and then the last one that we just talked about up above is, this is kind of works in reverse. If you are told that the intersection of A and B is simply the product of each of those probabilities, then that means, okay, then this means that events A and B, they must have been independent of one another. Okay, they must have been independent of one another. Okay, so it's kind of working in reverse. If a problem would tell you that this is true, then you can assume that they must have been independent. Okay, all right, there's a few probability problems to kind of wrap up this chapter up here. This is referring to consecutive probability. It says here 14% of the U.S. population are left-handed. Okay, so I always like to write down the information that I'm given in the problem. So we're saying 14% are left-handed, so I'm going to label that as 0.14. Okay, it says if you randomly selected 5 people from the U.S., find the probability that all 5 of them are left-handed. Okay, so essentially we're talking about the first person, the second person, the third, all the way up to the 5th person would be left-handed. Okay, and these are independent events. If you're left-handed, like if I know that the first person I select is left-handed, that's not going to have any bearing on whether the probability of the second person is left-handed or not. Okay, if I'm randomly choosing them from the whole U.S. population. Okay, so I'm just going to multiply that times itself 5 times. You also could simply just write it 0.14 to the 5th power. Okay, that is going to come out to be a very small number, so small that it is actually in scientific notation. That just means we're going to take that decimal point, we're going to swing that decimal point 5 places to the left, and roughly, it's a very small percent, about 0.5% chance of 5 randomly selected people from the U.S. being left-handed. Okay, not very high odds there. Okay, so this is kind of an example of the multiplication rule because we can logically conclude that, you know, each of these would be independent events there. Okay, underneath this, this is bringing us back to a very, very important point in probability, okay, and that is this phrase, at least one, okay? Specifically, it has to be at least the number 1, okay? Now, we touched on this in an earlier section, I believe, okay, and we said we use the rule of complements to kind of answer probability statements when you need to find the probability of at least one thing occurring in a bunch of things, okay? So here's the formula that we had discussed before. We said that the probability of at least one of something happening is actually the complement to the probability of none occurring. Okay? Because when you think about what at least one means, at least one means greater than or equal to 1. Well, the complement to greater than or equal to 1, if it's not 1 and it's not bigger than 1, then we're talking about being none. Okay, I mean, their only other option is 0. Okay, so if it's not at least 1, then it has to be none. So if you're ever asked this question and you know the probability of 0 or none, you can take 1 minus that, and that will give you the probability of at least 1. Okay, so we just want to keep in mind at least 1 and none, those are complements or opposites of each other. Okay. All right, so let's try to put this in action here with this example that's revisiting. In 1986, the Space Shuttle Challenger exploded on takeoff and all 7 crew members were killed. Following the disaster, scientists and statisticians helped analyze what went wrong. They determined that the failure of O-ring joints in the shuttle's booster rockets was to blame. Suppose that the probability that an O-ring fails is 0.023. Okay, before I read any further, I am going to write that down. The probability, now it said "and," meaning singular. The probability that one failed O-ring, okay, of one failed O-ring is 0.023. Okay, it says the shuttle, though, had 6 O-rings, and they all actually needed to work in order for a successful launch. Okay, so what that means is if just one of them fails, it would not launch properly. It says if O-ring joints succeed or fail independently. So they're telling you that each of the 6 O-rings functions independently of the other. So if you knew that the first one was successful, it doesn't have any bearing on what the second one, each one is completely independent. We are asked to find the probability that, oh, there's the phrase, at least one of the O-rings fails. Therefore, the shuttle would explode. Okay, they all have to successfully be successful here in order for a launch to be successful. Okay, so if the odds of an O-ring failing is 0.023, the odds of one successful O-ring would be the complement to that, okay? So that would be 1 minus the 0.023 or 0.977, okay? Now the question is, what's the probability that at least one O-ring, now here's the catch though, at least one O-ring of the 6, there are 6 O-rings, fails, okay? Because there are actually 6 altogether here, right? So what we're going to need to do is we see this phrase, at least one, and so we want to say, well, we could calculate that by doing 1 minus the probability that none, again, of the 6 fails. Okay, none of the 6 fails. So in other words, we're looking for 1 minus the probability that all 6 are successful. Okay, if we're saying none of the 6 fails, we're saying all of the 6 are successful. Okay, now let's look back at the information. We know the probability of one O-ring being successful is 0.977, okay? But I'm talking about 6 of them in a row all being successful. So I need to be multiplying 0.977 times itself 6 times, and that is what I'm subtracting off of 1. Okay, so that ends up being, I think we subtract 0.8697, which would give us 13.03% chance that at least one of these O-rings is going to fail and this shuttle will explode, which that sounds like a really high probability when we're talking about space shuttles exploding here. But we would just say that there is a 13.03% chance of at least one of the 6 O-rings fails and the shuttle explodes. Okay, this is really tricky, this concept of the probability at least one is 1 minus the probability of none, and what made this kind of extra difficult is the fact that we had to put that exponent right there because we were talking about the probability of at least 1 out of 6. Okay, so that's why that exponent had to go there. Okay. All right, and then our last example on these notes is kind of revisiting this idea of independence. They give us a couple of probabilities here. One is that the probability of event A is 40%, and the other one is the probability of event A or B occurring is 60%. Okay. So the question is, find the probability of B if A and B are mutually exclusive. Okay, so let's take the information we're given. We know on the formula sheet there is a formula for the union of A and B, that's the OR. Okay, this is how it looks on the formula sheet. Okay, well, we are given that up here in the problem that the union is 0.6, so I'm going to go ahead and replace the left side with 0.6. I'm also given in the problem that the probability of A is 0.4. This part here is asking us to find the probability of event B, so I'm going to leave that as my variable. And it mentions here if A and B are mutually exclusive. Mutually exclusive means the probability of A and B occurring at the same time is 0. So I can fill a 0 in there, and then I can just solve this equation for the probability of B, and I get that the probability is 20%. Okay, 20% here. All right, let's go ahead and try this last one. Again, they're asking us to find the probability of event B, but now they're saying assume that A and B are independent of one another. So let me go back to our formula here. This was the OR formula, the union formula on the formula sheet. Okay, we have a different set of assumptions now. We're assuming that A and B are independent. Okay, I'm going to go ahead and substitute the 0.6 on the left side and the 0.4 under A, and I'm going to leave the probability of B as my variable. Okay, now remember, we are assuming that A and B are independent. Okay. Remember, if we're told that A and B are independent, that's where earlier on the notes back here we said, I believe it was right here, that if A and B are independent, their intersection can be found by just the probability of A times the probability of B. So if we go back to this problem, we're told they're independent. So that means I can replace that with the probability of A times the probability of B. Okay, well, we know the probability of A. I'm going to go ahead and subtract this 0.4 from that side here. Okay, and now I'm going to replace this probability of A with 0.4. So essentially here we have 1 probability of A minus 0.4 probability, 1 probability of B minus 0.4 probability of B, which leaves us with 0.6 probability B. I'm just subtracting those coefficients. I'm going to divide by 0.6, and that's going to give me the probability of event B being essentially 1/3, or 0.33 repeating. You can see at the bottom here, here's all our summaries of all of the formulas. Only a few of these are on the formula sheet. Okay, I mentioned those if they are on the formula sheet there. So you can look those over. We need to be familiar with those. Here's kind of a summary as well as some really great strategies to try to keep in mind if you are stuck on what to do on a probability problem. These are things you could always try. See if there's a formula that would work on the formula sheet. Try making a Venn diagram. Maybe put the information in a two-way table.